everyone, welcome to our atomic radius video. But before we get started, I want to remind you that this is meant to be part 2 of a 3-part video series. So if you haven't already watched the first video on effective nuclear charge, please pause, go back and do that, and then come meet up with us in just a second. Otherwise, make sure you're fully aware of what effective nuclear charge is. So now, in this video, what we are going to address is what's called atomic radius. So how big is the atom? That's essentially what we're trying to do. And so the first thing that we need to figure out is we need to be able to kind of look at something and understand in the micro aspect what is actually going on with an atom. So let's just look at hydrogen, the simplest atom that we could possibly look at. So we know we have a nucleus here. The atom for hydrogen has 1 proton, so we have a +1 charge here. And then on the outside, we have 1 electron. Very simple. So we have a positive proton in the center, we have a negative electron on the outside. And so at this point, hopefully we're all very familiar with the fact that opposites attract, and so that there is a very, very strong electrostatic interaction between that proton and that electron. And so we would write there is a proton-electron attraction. And so what we need to keep in mind is that if we assume that our body is the atom, our nucleus, our core, that's going to be where our protons exist. So if we have a +1 in our center, right here in our core, and then we have a -1 out here on the outside, what we see is a very strong electrostatic interaction of that negative to the positive. And so when these two things are attracted to each other, essentially what happens, because that nucleus is grounded, we bring the electron closer and closer and closer to our nucleus, or closer to our system. So let's change our example here. Instead of looking at +1, let's look at helium, something that has a +2 at its center. So let's just redraw. Here's our nucleus. We have 2 protons here in the center, so we have a +2 charge. And then on the outside, I'm just going to draw a circle just for simplicity of our diagram. We have 2 electrons. So I'm just going to write here's one and here's another. And again, this is not what it actually looks like, but just for drawing this for simplicity's sake. Okay, so now what we have is a very strong electrostatic interaction on helium. So it's, again, same example. Our core is right here, so we have a +2 here at our core, and then there's 2 electrons on the outside, so a -2 on the outside. So think about that. +2 center, -2 on the outside. And compare that to what it would have been like with 1 in the center, 1 in the outside. So here, it's a proton-electron. They're attracted to each other. Very strong electrostatic interaction. But now we up it. So we go to 2 electrons, 2 protons. Now they are greatly attracted to each other. That whoosh, they are pulling those electrons in as fast as they possibly can and as close as they possibly can. And just think about what would happen if you had a +7,000 in the center. Such a large charge that they're going to pull any electrons that they possibly can in the inside. Now, there's a lot more crap that goes on with all of that, but just remember, we're trying to look at this topically globally right now. So let's compare this helium, our neutral atom helium, to something like a helium cation. So the center is not going to change. The nucleus is always going to have +2 charge for helium. But now on our outside, what we've done is we've removed an electron. So now there's just 1 electron, okay? So we have a +2 charge in the center and a -1 charge on the outside. +2, -1, oh my good gravy, they are going to pull that electron in faster and closer than you could possibly imagine. So instead of drawing this the way I have, where our circles are the exact same size, what I really should do is kind of draw that to scale. So instead, what would happen, instead of that electron floating around the outside, it is brought so close that this radius, which is lopsided, pretend it's more centrally located, but basically that electron is pulled in, so we have a teeny, teeny, tiny radius. So what we always see is that when we go from a neutral atom to a cation, we see this great change in the radius. It becomes smaller and smaller, and that's strictly because we have such a large positive charge in the center and such a small negative charge on the outside that we're able to whoosh, pull that in as closely as possible. Now let's go the other direction. So instead of taking away an electron, let's add an electron and make some really weird element called a helium negative. Probably doesn't exist. So now what we have here is our nucleus at the center. We have a +2 charge. Again, that hasn't changed at all. But now we have 3 electrons on the outside. So I'm just going to give this away completely. 3 electrons on the outside. Oh my goodness, this thing is gigundo. Okay, yes, that's a technical word, gigundo. And so what we see here is the exact opposite. So when we add an electron, it basically defeats the purpose of the radius, right? Adding an electron does not pull it closer. It doesn't say, ooh, -3 + 2, it pulls it closer. No, because now what you have are even more, remember, you can never forget about this part, electron-electron repulsions. So before here, we took away that electron. All those electron-electron repulsions are gone. So the only factor is this positive center and the negative outside. But now here, we've added another electron to the system. So not only are these electrons trying to get to the center with this huge attraction, they have to overcome this battle of this huge repulsion of electron to electron. And so what ends up happening is we see that these anions end up being significantly bigger or fatter than the neutral element. And so let's kind of draw this out to make it a little bit more to scale. So essentially what we see, if we had a neutral element, let's just say Z, okay, Z, here's neutral, here's the cation, and here's the anion. To scale, it would be something small, something bigger, and something much, much bigger. And this is going to always be the trend. And so I'm just going to put radii here. I don't want to put atomic because this was the only one that's actually we could really call an atom. I would much prefer to call these ions and ions, okay? So hopefully what you can be able to do from looking at this video is be able to kind of understand what atomic radius is, but in the context of effective nuclear charge. You need to remember that there's that concept. There's this positive piece where we have the pull, that attraction of proton to electron, and then that push, that repulsion of electron-electron. And all of this comes together with the atomic radius. So now, aside from comparing neutral to cation to anion, we also need to be able to have a generic trend, so a macro perspective. And basically what we see for this, okay, is that as we go down a group, we definitely increase. And that is essentially like putting on a coat, okay? So here you are at the first level, you're just wearing your underwear, whatever. Now you add on some clothing, you put on another shell, okay? Another shell, you go down. So you add some clothes, okay? So now you add another shell on, this is your sweater. Now you add another shell on, now you've got your jacket on. Now you've moved to Michigan and you need your parka. Now you've moved to Alaska and you need a giant sleeping bag on top of that. So you have to think about this is really, really tiny, very small, and as we go down a group, we're layering, adding a shell, and there's no way you could possibly add a layer of energy or electrons without getting bigger. So as you go down a group, our radius gets bigger. Now, we need to talk about across a period. And so what we see is that as we go this way across the period, we see that our effective nuclear charge increases, okay? It gets bigger and bigger and bigger, meaning that we have a more positively charged center over here on this side. So what that means is that we actually see our trend go like this for radius. So it's bigger over here when we have a smaller effective nuclear charge, and it's smaller over here where we have a bigger effective nuclear charge. So hopefully this is all clicking. Hopefully this is all clicking. It always comes down to the protons, okay? So if you were to draw a gorgeous periodic table and do a very generic trend, we would say that the biggest corner is down here. These are your fattest, biggest atomic radii. And so what I like to remember is that right here we have this beautiful girl named francium, and francium is always fat. Okay, that's all I've got for you. Hopefully this is starting to make more sense. Please stay tuned. We've got one more video for this series where we're going to go into ionization energy. Have a great week. Take care of yourself. Drink water.